We just finished reviewing drawing Freebody diagrams. Freebody diagrams show all the forces acting on an object, but we don't draw Freebody diagrams, or at least typically, as an end in itself. We don't draw Freebody diagrams for the sake of drawing Freebody diagrams. We draw them as a tool to help us to solve what we call multi-force problems. Multi-force problems are problems where there is more than one force acting. And all the force problems that we've dealt with so far in the past week, there's been one force acting, whether it be friction or an applied force or whatever. Now we're going to deal with those problems where there's friction and the applied force and whatever forces. So, what do we got to do? Whenever we see a problem where there's more than one force acting, we want to solve it mathematically. What are we going to do? Well, we're going to start off by drawing that Freebody diagram. Remember, that's the reason why Friday and earlier today we were drawing those Freebody diagrams, to get us good at that. Now it says cancel out any forces that you can. What do we mean by that? What do I mean by cancel out any forces that you can? Give me two forces that I could typically, not always, but typically cancel out. Gotcha? Gravity and normal force, right? Caitlin, why am I going to cancel out gravity and normal force? Like typically, at least.
Because the weight is the gravity.
Yep.
And it's equal to what's pushing up.
Good, because it's equal and opposite to what's pushing up. So if you have 10,000 newtons pulling down and 10,000 newtons pushing up, hey, just get rid of them, because the net force between the two of those at least is zero. So let's not complicate our analysis by including those. We're still going to draw them on the Freebody diagram, but we'll just cross them off. We'll cancel out or cross them off if they balance each other out. So that leaves us with less forces that we need to end up dealing with. All right. Whatever forces we have left, if they're in one dimension, and by that I mean if they're on the x-axis or the y-axis, but not both. If you have a net force going to the right and a net force going up, you can't deal with it this way. Okay, we're going to learn to deal with those in a few days. If all the forces that are left are either on the x-axis or on the y-axis, but not both, then you're going to do the following. After you've drawn your Freebody diagram, you're going to set F net equal to, well, I say F1 plus F2 plus whatever, but it's really F net is equal to FA plus FF, whatever forces you have that haven't canceled out. Right? I think it was it Sarah that told me? No, it was Venture that told me that normal force and gravity often cancel out. Caitlin said because they're equal and opposite. We're not going to include those here, right? Because they've canceled each other out. We're going to include the ones that haven't canceled each other out. So we're saying F net is equal to the sum of all the forces, the total force. That's how we defined F net the very first day of this unit, right? F net is the total force acting on an object. Hey, what's F net also equal to, besides the sum of all the forces? Jacob? F net is also equal to what? You know this. We make F, in addition to being the total of the forces, F is equal to what? You're thinking it. You're thinking the right thing. Well, it could be. Yep. Mass times acceleration. Does that make sense? And F is equal to m times a. So what we're going to do in step 2 is say, well, if F net was equal to F1 plus F2 plus F3, then MA is also equal to F1 plus F2, so on. Then you're going to solve it. You're going to plug in your numbers, and you're going to solve for what you're looking for, which often, although not always, works out to be the acceleration of the object. So in other words, listen, if you got one force acting, F is equal to m times a, solve for the acceleration. If you got 14 forces acting, then what you got to do is add up the 14 forces, and then say F is equal to m times a. But you do have to be careful that when you're adding these up, you pay attention to direction. If you got this one to the right and this one to the left, F1 is positive and F2 is negative. If you have another one like this, well, then you can't solve it this way. You got to do something else that we'll look at in a few days. All right? All right, here's a problem from page 132 of your textbook. It says 2 people, A and B, are dragging a canoe out of a lake onto a beach using light ropes. Each person applies a force of 60 newtons forward on the rope. There's a force of friction by the beach on the canoe of 85 newtons backwards. Starting with the free body diagram, calculate the net force. This one's actually, it's a good intro to this because it's actually a little bit easier than average because we're not looking for the acceleration. But we'll start off the same way still. First thing you should do is what? If you have more than one force acting on a problem, you should do what? Draw a free body diagram, right? Now, we can draw it looking from above or we can draw it looking from the side. Okay, if we draw it looking from the side, then we've got, we'll call it FA, 60, FB, 2 guys both pulling it with 60 newtons, and then we have a force of friction. It's backwards like this, a little bit longer than FA and FB. We'll call that FF, is 85.0 newtons. We also have gravity and the normal force. But what do you know about gravity and the normal force? They cancel each other out, right? Get rid of forces that are equal and opposite. Now, some of you may look at the diagram that you see up on the board right here, the original diagram, and just say, oh, look, I can draw it looking from above. If that's the case, there's FA, there's FB, and there's FF. It can't really, on this one, looking from above, draw the normal force and the force of gravity, right? But that's not the end of the world. It's not the end of the world because they end up canceling out anyways, right? So whichever way you want to draw it works in this case. All right, what's my next step? What's my next step? Erica, what's my next step? What's my equation? F net is equal to what? Good. F1 plus F2, or in this case, we're going to say FA plus FB plus FF. Do we see why that F1 plus F2 was kind of the general form of it, right? We renamed F1 to FA, FB, FF. Okay? F net is equal to FA plus FB plus FF. Now, if I was looking for the acceleration of this, which I'm not, then my next step would be to sub in m times a for it as well. But since I'm just looking for the net force, let's not replace that with m times a. What's the value of FA? What's the value of FA? Haley, what's FA here? 60. What's FB? Yep. And what's FF? Close. Oh, so close. Where's my error if I write down 85 newtons there? Yes, it's negative because it's to the left. Yeah, 60 and 60 are both to the right. 85 is to the left, so we got to make sure we make that a negative value. Good. So 60 plus 60 is 120. Then we add negative 85 to that, and it gives us, I think, 35 newtons. So my net force here would be 35 newtons. If I was looking for the acceleration, then I would set that equal to m times a and solve for a. Right, we're getting there. You got more than one force acting on a problem or on a question or on an object. More than one force acting on an object. What are we going to do, Christian? First thing. When we have more than one, what do we do first here? When we have more than one force acting, what do we do?
Make a force body.
Yep, make an FBD, a free body diagram, force body diagram, whatever, right? As long as when I say a free body diagram, you know what I mean by that. Okay, I don't really care what you call it. Okay, draw the free body diagram, draw the FBD. Once we have the FBD drawn, the free body diagram drawn, McKenna, what do we do after we have this diagram drawn? And after we have things canceled out, if that's appropriate, what do we do? Yeah, use the equation. F net is equal to the sum of all the forces, whatever those forces happen to be called. F1, F2, FA, FB, whatever. And then sometimes we need to replace it with m times a, but not always. In this case, we didn't. Okay? Plug in the numbers and solve. All right, let's take a look at the two questions on page 132 for the next few minutes, please. Have a look up here. I want to do question number 1 as a group here. It says 2 dogs, A and B, are pulling a sled across a horizontal snowy surface. Dog A exerts a force of 200 newtons forward, and dog B exerts a force of 150 newtons forward, but there's a force of friction of 60 newtons. The driver attempts to slow down the sled by pulling on it with a force of 100 newtons backwards. Starting with the free body diagram, calculate the net force on the sled. So question number 1 here, let's draw the free body diagram. Here's my sled. It doesn't matter whether it's a dog pulling or a tow truck pulling or a person pulling. That makes no difference. So we don't need to draw the dog here, either dog. Right? All we need to draw is the sled. Tell me the forces acting on this sled. Tell me one of the forces acting on this sled, assuming that it's moving, assuming that forward is to the right. Peter, what's one of the forces acting on this sled? So, okay, so let's call it F. We'll call that FB. Is 150 newtons. Okay, good. What else we got? What else we got? Leo, what else do we have in addition to that dog? Yeah, now I'm kind of running out of space over there, so I'm just going to draw it down here. FA is going to be a little bit bigger number, right? Or a little bit bigger vector because it's a bigger number. It's 200 newtons forward. What else we got here? If you know a nice, easy answer, then give me the easy answer so I don't call on you randomly, right? Yep. Yeah. I got FF, and that's going to be a small one, right? And that's going to act backwards here. Probably should actually be smaller than that, but draw it too much smaller than that, we're not going to even see it. Is that it? No, I got 100 newtons here, Megan. What else? Yep, to the left, good. It's to the left. So it's 100 newtons, I don't know, something like this. We'll call that FD for the force of the driver is 100 newtons. Although really you can call it whatever you want, right? Call it F1, whatever. Is that it? It's not really it. It's all the important ones. Why do I say that? Why do I say it's not it, but it is all the important ones? Leo, what am I missing here in my diagram? It ends up not really mattering too much. Good. The normal force and the force of gravity. Gravity's acting down, the normal force is acting up. But why don't they matter too much? Yeah, they're the same value, they cancel out. If you forget to draw them, it's not the end of the world. We want to be in the habit of drawing them because there's going to be lots of problems down the road where they matter. But in these cases, they're canceling out so they don't matter too much. Okay, what's the next step? What's the next step? Tiana, what do we do next? After we've got our free body diagram drawn there, after we've canceled things out. Yeah, and the equation is? Yeah, it's all of those forces. FF plus FD plus FA plus FB. Now, if I was looking for the acceleration, then I would say m times a as well, but I'm not, so I'll just leave it as F net. Friction, what's the value of friction here? Ryan, what's friction? What do I sub that in as? Almost. Y negative, Ryan? Good. Negative 60 to the left. FD I got to sub in as... Lucas, what do I sub in as FD? Yeah, negative 100. Now, notice I'm adding the negative 100? You could subtract it, right, because it's exactly the same thing. I just like to be in the habit of adding because that's what net means. Net means total. And when I find a total, I add. Okay? So it's negative 60 plus negative 100 plus, and then it's FB plus FA. So we're going to say 150 plus 200. We add those up. Negative 160, negative 10. I think it's 190, isn't it? 190 newtons? Yep. 190 newtons, and positive means forward for us. Good? How many people are still working on question B? Okay, I'll give you another couple minutes to finish up question B. All right, let's have a look at question number 2 here now quickly. It says, in a tractor pull, 4 tractors are connected by strong chains to a heavy load. Load is initially at rest. A and B pull with 5,000 newtons and 4,000 newtons east. C and D pull to the west. Friction is 1,000 newtons. All right, so let's look at this tractor, or let's look at this load here. It's being pulled. Which way is it being pulled? It's being pulled to the right or to the east with 5,000 newtons. We'll call that FA is 5,000 newtons. FB is 4,000 newtons. Now we got C and D, 4,500 and 3,500 to the west. So let's make FC about like this to the west. FD is 3,500, so it's going to be about like this. Any other forces acting here? We do. In fact, more than one of them. What other forces do we have acting here? Do you know? Good. We have the force of friction acting. It's got a value of 1,000 newtons. Which way is it going to act? Do you know? How do you know it's going to act to the left? You're right, by the way. But how do you know that? Okay. JC, got a little bit stronger there?
Is it because if like ignoring the force of friction, like the right tractors are like pulling harder?
Yes. In the absence of friction, look at what we have up there right now. We have no friction drawn. No friction drawn right now. What's going to win? East or west? East. So in the absence of friction, it's going to move to the east. Well, then which way is friction going to act? It's going to act to the west to resist the motion. So, Tino, you were right. It is to the west. Let's make that FF is 1,000 newtons. Now, we should also have a force of gravity acting down and a normal force acting up. But what do we know about those two forces? They're going to cancel. Somebody said that. Yeah, they're going to cancel. Good. So now let's say F net is equal to the sum of the forces. That's our next step. FC plus FD plus FA plus FB. By the way, if I change the order of these and made it FABCD, would that be okay? Yeah? What's 1 plus 2 plus 3? 6. What's 3 plus 2 plus 1? 6, right? It doesn't matter what order I add them in. I just kind of drew them in the order that I, or wrote them in the order that I drew them there. FC will be negative 4,500. FD will be negative 3,500. Oh, I missed friction. FF will be negative 1,000. FA will be 5,000. FB will be 4,000. What's the net there? Adds up to give me 0 newtons. If the load is initially at rest, is it going to start moving? Is it going to start moving? Is it? No, because an object at rest will stay at rest until acted upon by an unbalanced force. This is not an unbalanced force. If I had this object that was moving, if this was moving, would it stay moving? Yes, at a constant speed. Despite the fact that all these forces are acting, there's no net force, so if it was moving, it would stay moving at a constant speed. Remember, it's in static equilibrium because it's at rest, it's going to stay at rest. If it's in translational equilibrium, which means it's moving with all the forces acting on it, balancing out, then it's going to stay moving at a constant speed in a straight line. Is that all right? Okay, we'll pick this up where we left, where we're leaving off here now. We'll pick this up tomorrow.